Hello everyone, so welcome to the IBM Modeler tutorial. We're going to go through the main and basic features of IBM Modeler, and to be more specific, I have listed the agenda of this demonstration. We're going to start with the introduction of the tool itself, and then we start working with a source node. Again, I'm gonna cover the basics. In some cases, I try to go a little bit further, hitting the intermediate level as well. Then after that, we're gonna start exploring the data, see what needs to be done in terms of data pre-processing. That includes imputing the missing values. First of all, introducing and defining them, and then imputing it. Then we will fix the noises as part of the data cleaning. We'll do further pre-processing, which includes binning and then partitioning or splitting the data for predictive models, and also balancing it for predictive models. Then we will build at least one decision tree and neural network as part of the supervised learning experiment. Also, we will touch the unsupervised part by trying out some k-means clustering models. We will look at the results of all these models. This includes the confusion matrix and ROC curves. For the classifiers, we will try to plot some graphs, and finally see how we can reuse the models, or basically how to deploy it. I quickly go to the IBM Modeler screen that we have here. So IBM SPSS Modeler is statistical and data mining tool that you can use to build both predictive and descriptive models. As you can see, it has a big white canvas in the middle. On the right hand side, you have a panel that you can have access to some of the artifacts that we will build, and we will see that they will be added during the time that you work with them. You can start organizing your project following the CRISP-DM methodology that it has provided for you here. And finally, most importantly, is this lower panel that you can have access to all the nodes that are basically the items that we use to do any action in IBM Modeler. So yes, what if I want to recap? We have a project. Inside a project, we build a stream of nodes, which you will get either you're familiar with, or you will get familiar while we go a little bit further. And the nodes are in different types and shapes that again, we will introduce them as we move forward. But just to have a sense, we have different types of nodes. Some of them are called the source nodes, which are shown in the circle. It's a way that you can read the data into the modeler. And then you have the pre-processing nodes, which are under the records operation and field operations. They look as hexagon. And the records operation are basically the pre-processing that happen on the records, and the fields operation, as you've understood, are the pre-processing actions happening on the columns or on the fields. We have the graphs that they look like a triangle. The models are in pentagon shape. And then we have the output or evaluation nodes, or the export nodes as well, that they're in the shape of square. So these are all the nodes that we have, a lot of different features that have been built in IBM Modeler. And basically the idea is that you have a canvas here, you start adding the nodes to the canvas, and you connect the nodes one after the other, and it starts driving the data based on the settings that you provide from the first node to the second, the third, and goes down the stream. Okay, so the data set that we're going to use today is basically the same data set that we had in our lab session, the bank data Excel file. I have modified it a little bit. As you know, it's not a huge data set. It's just for the sake of trying out the IBM Modeler and run some quick models and see how it goes. Okay, so because it's an Excel file, from the source tab down here, we have the option to add the the Excel source node to the canvas. In case that you're going to have a CSV file or any other text delimited file, this variable file here would be useful for you, and if there are databases, of course the first one. But for the CSV files, I'm just going to open this and show it to you. Then we'll go back to the Excel source node and continue our work. So in this window, you will load and select your CSV or text file, and you have all the settings here to define how you wanted the file to be read. Most importantly is down here, the field delimiter. If it's a CSV or an actual CSV, which is comma separated, so you need the comma to be checked here. If it's not, in some cases, I see that the text files are like semicolon delimited or other items. You have the chance to provide it in this text box and just say, like, for example, I input semicolon, and it will start reading your file, considering that the values in each row are separated using semicolon or any other, like pipe delimited or anything else. A lot of the data sets are in text and CSV format, so this would be very useful for you. But in our case, we don't need this node. We need an Excel source node that we're gonna use here. The file type, either if it's a 2007, 2016 Excel file, the XLSX, or it's the older versions, you can select that. And to import the file, we select this browse button here. You select your file, hit open, and it will add it here. You can modify the other settings. In our case, the default is good enough. Everything is on the first spreadsheet, and there are no blank rows, and we do have the column names in the first row. So what I would suggest is that every time that you basically set up a source node, make sure that you hit the preview button to see that the data is actually the correct one that you wanted to work with. It will read the first 10 rows. In this case, we see that, yeah, we have all the columns that we wanted to, and it all looks good. So we just close this. And yeah, so that's how easy you can just read the data in. But before we go further, there are other tabs here on the source node that can be useful. The second tab is called Filter, and here it lists all the fields or all the columns or variables that you have in a data set. Let's say there are some columns in your data sets that you absolutely don't need them. They were there for whatever good reason as an intermediary purposes, but you don't need them in your analysis. So you can just filter them out from the very beginning here, so you won't see them later on when you start working with this data set. In our case, we need all of them, so just leave this. The third tab here is called types. This is very important information in IBM Modeler. A lot of the settings that you will provide and you will need in the modeling section are dependent to what you have defined here. So the fields or the variables in IBM Modeler, they have a measurement type. Well, of course, you might call it something else like the data types. Either they're continuous or categorical, but you have to keep in mind that when let me expand this. You have to keep in mind that the categorical ones have some subtypes which are called flag, nominal, and ordinal. Flags are basically the binary, the yes and no, the true and false variables. Nominal are the ones that have categories that you cannot put them in a conceptual order, like colors, let's say. Ordinal are the categories that they do have a sequence, they have order inside them. Like for example, the grade for students, like A, B, C. A is bigger than B, and so they do have a natural order in them. That is one thing. The other thing is that the last column is called role. Each field plays a role in the project, in the stream of nodes that we're going to build. By default, they've been all selected as input, but so that means they're going to be considered as input variables inside the models that you're going to build. But let's say a field is not an input, it's going to be a target variable, which we also call the label of your classifiers. You have to select it as a target here. In this case, like I've selected the ID. ID is a record ID. It's neither input or a target. Okay, we will get familiar with some others as well while we move forward, but the important ones, the input, the target, and the record ID that we just saw right now. So, but before you start manually setting all this information, what I would suggest is that you just select the read values button. What it will do, it will read some few values from each field, and it tries to predict the measurement and role. Let me expand the window a little bit here for you to see. As you can see, for the ID, it considered as a typeless measurement. Okay, and then for the others that were continuous, they just left as continuous. The categorical ones were actually changed to one of the subtypes, nominal or flag. The way that you can verify it is by seeing the values here. So you're seeing a range of values and numbers. So it's okay that you consider that as a continuous. Let me go down here. You can see yes and no's, so it's like a binary value. So it's good that it has selected flag. All right. I can show you an example, and this will help us start exploring the data. For the gender that I have here, it has selected as a nominal. And the reason that I look at it, I see that 4 distinct values have been observed under this column. While I didn't expect that, I just expected to have like female and male and select this as flag. But it actually found more than 2, so it changed it to nominal and provided all the values. So I'm just going to leave that there for now. I'm not going to start touching it. One last thing before I leave. Please remember that these settings that we provide here are basically the default settings for your data set. What does that mean? Later on, depending on the model that we're going to build, you might want to change this information. You might want to filter out, you might want to change the roles and all that sort of stuff. But this would be like your default settings that you want to provide, And later on, if any specific thing wanted to be changed, you just touch those. You don't want to touch everything all the time. So in this case, the last field, which is approved field, is the label of on the data set. So I'm going to select it as a target variable. And yeah, that's it. So I click OK and I close it. So there we go. We have the data set that I want to work with here. And now I want to explore further and see what is exactly inside my data set, the distribution of the value, the quality of them. So under the Output tab, we do have a data audit node that we can add it to Canvas. And the way that you start building a stream is that you right-click on the first node, you select Connect, and then you hit the destination node or the second node. And it will build an arrow between these two nodes. That means it's going to flow the data and apply the settings that you have here, and then goes to the next node, which is a data audit node. And this data audit node is going to help us to explore the data further. So I double clicked it, I opened this data audit node. Everything as the default is good enough for us. So let's hit the run button and see what we have in our data set. Okay, so it actually plots a thumbnail of the histograms that you have for each field. Shows a minimum, maximum, the mean, standard deviation, the number of valid cells or values under each field. Keep in mind that I had 600 records. So here it's telling me like you have 600 valid values, but there are 4 unique or distinct values. This was the issue that we saw for gender, and we need to dig into it and see what's going on. But then here for age, I don't have 600 valid values. I have 595. That means 5 of them either are missing or something wrong with them. And by the way, the minimum age is -1, the maximum is 555, which doesn't make sense. Okay, so these are the information that you want to explore and see what's going on, if these numbers make sense or not. Are you expecting it or not? And keep in mind that you can double click any of these graphs and it will show it on a bigger screen for you. All right, but what it's doing, this is a continuous field, so it has automatically put the values in buckets or in bins, and it's showing me the values. In case that you have a continuous field like this, like the age that we have here, we have a lot of numbers. Maybe this doesn't show you exactly where the data distribution in that field, especially if the minimum and maximums don't make sense and you want to have a more detailed graph. I'm gonna put this section on pause and just to expand the information on this part, I'm gonna minimize this window. So there is the graphs tab here, which you can visualize the information that you have. You can use it anytime based on what you need. It's not part of like the first or last section of your stream. No, anytime that you need to visualize something, you can use these graphs. And right now I need it because I saw the age field and the histogram wasn't very informative for me. So I'm just gonna add a histogram node. Let me just add it down here. And then I connect my data source to this histogram. All right, let's open this. Something wasn't quite right with the age field, and I want to build a more specific histogram to see what's going on. So I select age for the field, and let me go to options. Yeah, so I don't want it to put it into like bins. I just wanted to like have the normal width with a size of 1 because it's an age and they're all natural numbers. And then now run this to build a histogram with the units of 1. Okay, so as you can see, this looks a bit different. It's more specific than the previous one that we saw. I have a very strange value here. It's very off. I can see that I have a value below 0 to negative value as well. The rest looks okay to me. All right, so I close this window. I go back to I want to go back to the data audit window. So if I open this, it's gonna ask me to, again, how do you want to like run and open the data audit window? But because we already had that data audit window, if you go to the outputs here, okay, so the data audit that we kind of executed, yeah, perfect. So we can again open that window and get back to where we were looking at. So of course there's something wrong. The -1, the 555, they are not acceptable. They're invalid values, or they're noises that they cannot be fixed. They just have to be removed and nullified. With the gender, let me just double click this graph and see what's going on here. Yeah, I can see there are 4 values. Female and male look good. F and M. F and M are also noise. Okay, but these noise, I can anticipate that F, of course, probably meant to be a female and M to be male. And what I'm going to do, I'm not going to remove these noises. I'm going to fix them by replacing it with the correct values. Okay, everything else looks fine to me. The other thing that is important in this window is a second tab called Quality. If I move here, I can see some additional information such as the outliers or extremes. And then, like for example, for age, it says you have 1 extreme value. The difference between outlier and extreme, I mean, I'm not exactly sure how Ibm Modeler sets it as outlier extreme here, but by definition, when your data point, let's say it's a 2-dimensional data point, you only have 2 attributes. The data point is off on the x-axis, then it's extreme. When it's off on the y-axis, it's an outlier. I do have an example here that I can show you some graphs. Maybe that helps to understand it. Like, let's say this is an example scatter plot of the data point. It's 2-dimension, first attribute and second attributes. Like in this case, in example 2, the red dot the x value is within the common range of the other data points. All right, but the y value is kind of not following the trend that we can see on the plot. So this is considered to be an outlier. Okay, this data point. Then it can be like judged to be if this is an influential outlier or not. That means that if we don't consider this data point, how will the trend be? And when we add this or we consider it or include it, how will it affect this trend line? It's not going to affect in this case. As you can see, the two red lines are kind of overlapping, so it's not an influential outlier. But there's other examples in this screen which might be beneficial. Okay, here in the third example, the red dot is now off the range that we can see most of the data points are. In this case, this is considered to be an extreme value. Okay, but if we draw the trend line, we can see that it's kind of going toward the red dot. So it's an extreme value, but it's not an outlier. And it's not also influential because when we include that, the trend line is not being affected. There's another example down here that, yeah, you can see like the red dot on the x-axis is kind of off from the range, so it's an extreme value. If we consider the trend line, it's not close to trend line, so it's an outlier as well. In addition, it's an outlier data point that is influential because when we start considering it, the trend line starts to change the slope. All right, so this is just some like background information of okay, let me just open this window. The difference between extreme and outlier. Again, I'm not exactly sure how Ibm Modeler is on, because this is only on one attribute and this is like one dimension, and we just consider it to be synonyms. When it's an extreme, it probably could be an outlier as well. But anyway, no matter what, this is telling you that there is one value that is very off the range that you have. Of course, we saw the histogram. It was like that very large 555 number. So if you have outliers or extremes, I would suggest you go and check what's going on. What are those values? Are they valid values, or they are noise that you need to take care of them? In addition, if I go toward the end, there are other columns called null values, empty string, white space, blank values. All of this stuff are considered to be missing values. We see them as missing values, okay? No matter their type, we see them as missing values. Depending on your source node, or basically the source data set, type of the source data set, it might consider them as empty space, white space, or empty strings, or null values. But we will consider all of them as missing values that we want to fix them or impute them. Okay, so to recap, this data audit window will help you to start planning your pre-processing steps. So we saw some issues here with age in terms of the noises. We saw some noise on gender. We saw some missing values on age. One other thing is that we have the income. Although the numbers look valid, the range that we have, they make sense. But especially if we want to like build a decision tree, we might prefer to, instead of having a lot of these real numbers, we put them in buckets so that it deals with fewer distinct values. Because it's continuous, it didn't tell us how many distinct or unique values it has. But anyway, so these are the items that we're gonna handle as part of our pre-processing. So then now you have to start thinking of like, okay, so what has to be done first? And most importantly, what I would suggest is tackle the noises. All right. First of all, tackle the noises. The one that you think are valid, but they just fix them, replace them with the correct values. Then the ones that you believe are invalid, nullify them, kill them. Okay. And then after that, maybe you want to impute the missing values. Then if you want to put them into the bins or different things, we can do that and continue our work. Okay, so to do that, what should we do? Let me close this window. So we're going to start with the gender. Okay, so for gender, we had F and M, which need to be fixed with correct values. There are two nodes here, one called filler and the other one reclassify. Depending on what you want to do, you can use any of these two. The filler, just to show you how it looks like, I'm just going to add it, but I'm not going to use it in this example. What you can do, you can select one or more fields, and then you can specify a condition. Like let's say you want to say if the value was this character or this string, then replace it with something else. Okay. Then it will apply it to all those fields that you have selected here. In this case, I'm going to use the Reclassify node. And I'm going to connect the source node to Reclassify. What Reclassify does is that you can use it for this purpose or other purposes. But what it does is that, let's say you want to change the way that the categories in one of the fields are there. You want to merge some, you want to, I don't know, rename them, and etc. You can use this reclassify window. So in this case, I'm not going to create a new field. I'm just going to replace with the existing field. Okay. And I'm going to fix the noise inside the gender field, which we had the F and M's, which we didn't like. Okay, we select the field, we hit get, it will load all the original values. Okay, now I will start mapping to which value I want to change. Okay, so I'm going to change F to female. And then, well, let's see. A new item, or no. Again, female to female, then male, and then male. Okay. So the rest looks good to me. And then we can hit OK. At any point, you can always add another data audit node here. I'm just going to add this here. And let's say at this step, we want to see what happened to our data. We just connect the reclassify to data audit, and we run it to see how it looks like. Okay, now I can see for gender, there are two unique values, and the distribution graph that we see, it looks perfectly fine, female and male. So I'm happy with what we did for that, so good. So for the age field, we had invalid values and we had missing values, which we need to fix. In order to define the missing values, what you can do is when you were on the source node, okay, the third tab was types. And then this column is called missing. Here is a place that you can define what are the missing values in each of the fields. Especially after we explored the data, for the fields that there were some problems related to having a missing value, you better come and actually define specifically what those missing values mean. Okay, in this case, because I'm just going to keep the source data as is, if I wanted to go back and show something to you and compare to what we're doing step by step in the pre-processing, I'm not going to define the missing value for age here, although you can do it and it's perfectly fine. But because I want to keep this raw data, and if I want to go back and explore it again and compare it to how it looked like originally, and also I was working on one of the columns as part of my pre-processing steps, I'm not going to define the missing values here. Instead, I'm under the fields operation tab, I'm going to add a type node. Okay, the type node exactly looks like the same as the types tab that we just saw on the source node. Okay, exactly the same thing. But it's just like instead of applies it at this step, we're defining applying at this step. All right, so what we're saying was for age, we want to define what is the expected or correct range of values. And then anything out of that range, we want to consider as missing values. Okay, so what we do, we click on this cell under the missing column for the age field, and we hit specify. So here just shows you it's a continuous and has a real value, blah, 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 blah. Here we say specify values. When you hit this, you are defining this is the range that I consider to be like the valid range of the ages that we have. So in this case, I'm just going to say from 0 to, I don't know, 150, let's say, is my valid range of values. Anything outside of that is missing value. Or basically it's invalid and considered as a missing value. And okay, so when it checks the values to see if they're in this range or not, what I wanted to do is I wanted to nullify anything that is outside of this range. Okay, in addition to that, I want to hit this define blanks checkbox. So here you have the opportunity to specifically say which values are missing. Okay, let's say in a variable, everything looks great. All the values are in the good condition, and you expect everything to be from like 0 to whatever, all plus numbers. But then you are starting to have a bunch of -1s, and you assume that anywhere -1 was entered, that is probably there was no information there. So instead of like leaving it blank or as a null value, they just put -1 so that it's not empty. But in our case, we want to say like, okay, so that -1 is actually missing value to us. It doesn't have any information. It's not a valid value. So just put like -1 here. Okay. So this is a way that you can define non-null values that mean to be missing. Okay. or, which I'm not going to do it at this point, or let's say a specific range. You want to consider it to be like this range is not good, it's not valid, and any values in this range, I consider them to be missing. You define a range of missing values. By default, null is checked. Keep in mind that white space, especially if you're working with CSVs, it's very possible that you start seeing like empty string or white space cells. And sometimes IBM Modeler by default doesn't consider those white spaces or empty strings as missing values. It will show them in the data audit screen that, okay, you have like 5 empty string values, but it might not consider them as part of the missing values. So you have to come here, specifically say, if there are any white spaces, do consider them as blanks, which we consider them as missing values here. Okay, so please do pay attention to this, especially if you're working with text files or CSV files. We hit OK. It put an asterisk here. That means you've defined the missing values for age. Okay. So again, let me hit OK. And I just want to see by this definition what my data looks like. So if I again run a data audit on this, we're working on the age. Okay, so look at this. The minimum maximum change is 18 to 67. I define the valid range to be 0 to 150, but the values that we have in the data set within the range that I defined are from 18 to 67. This looks perfect. Okay. Now when I move to the quality type, I no longer see that extreme because that was out of the valid range. Now, if you remember, I had 5 null values. Now I have 7. That -1 and that 555 have been nullified and were added to the null values that we see here. Okay, so this looks great. Okay, what we need to do is to fix this missing value. The way that you do it is actually here. There are no nodes in IBM Modeler that can impute the data set. The way that you have to fix the missing values is basically here in the data audit node under the quality tab. For the field that has missing value, you just move over to this cell under the impute missing column and you click on this cell. It says, okay, do you want to impute the missing values? By default, everything is never. But what we do is that we say, yes, we wanted to impute any blank and null values. Okay. Then it will ask you what method you want to use to impute. If you're familiar with how these 4 different methods, 4 options that are provided here work, then you can just select and move on. But if you're not familiar and not exactly sure what will happen, just click on specify and it will open this window for you. Again, you can see, okay, impute when blank and null values, we did set that, that's fine. And you see the 4 different methods down here. If you select fixed, what it will do, it will replace the missing values with the mid-range number. All right. Or any other numbers that you want, the mean or the constant value. If you want to provide a random number, again, you have the chance here to select what type of distribution you want to use. You can even also provide a formula as an expression and say, like, for example, get this number and then multiply it with that and then etc. And to replace it, let's say you want to build this number using other columns or other attributes that you have, you can use this expression. What we're going to use is the last option, which is called algorithm. And there are only one algorithm here in Ibm Modeler, the cart decision tree, the classification and regression tree, basically. There are other algorithms out there. One of the popular ones is the KNN impute algorithm. It uses KNN. In this case, it's going to use cart, which is fine for us. We select this, hit OK, and then yes. So it says impute the missing here. It looks good. Now, how can we actually execute this? Please pay attention that there is a menu item here called generate. We select that, and there are some options that we have: missing values super node, missing values filter node, missing values select node. Depending on the method that you have selected here, you might want to go with any of these nodes, but with one of these items. But because we went with the algorithm and it's more sophisticated than just any of these simple nodes, we're going to go with the first option, which is a super node, and it's going to take care of all the magic of imputation for us. So yes, select the first item. It will ask you which fields to consider when it wants to basically run the algorithm to impute the missing values here. We're going to consider, we want to include all fields, and then 10% sample size. It will take a 10% of your records, and then based on that, it will impute, which is fine. If your data set is small, you probably better to go with a larger sample size. If your data set is huge, the 10% should be enough. But for now, we're just going to leave it as default. Hit OK. And nothing happens on this page, but it will close it. It will add a star node, which is a special node that we didn't see down here in the panel. This is called a super node. Okay, so let me disconnect this. This was just like a dummy data audit node that we're going to use from time to time. What we do is that we say, bring in the super node in our stream, and we can open it and see what's inside. It doesn't show anything much here for you, but if you are interested to see what happened, you can hit this zoom in button down here, and yeah, that's what it is. It's basically a substream that it did build a cart model. We're not still familiar with this golden nugget, so I'm not going to go further because later on we will see this when we build models. But just to have a sense, what it did, it used the cart algorithm. It built a prediction or a predictive model, and the models that are built are shown as golden nuggets. And then it tries to predict the values for the missing values and replace them. So that's how it imputes them, and then it takes care of the other steps required to impute them. And yeah, so that is the super node that is going to impute the age field for us. So how can I get out of here? By the way, on the tabs, under the tab called models here, we can see one model has been built. This model is again for the missing value imputation model that was created for us automatically. Click on streams, and then this substream that we were looking at, just click on the parent, and then it will get out of that and we'll come back to our main canvas. Okay, can hit OK, we close this. So you're familiar with this practice, what I do at every step, especially at pre-processing, I want to make sure everything looks good, nothing bad happened. So I connect it every time to a dummy data audit node that I have there. Look at it. So the range looks good. And yeah, so 600 valid values, and everything looks to be fine. Everything is 100% complete, and there are no missing values. So we're good. One last thing that I want to do as part of my, okay, let me go back to the agenda that we had here. So yeah, we went down to 5. Now we want to bin one of the fields and make sure that it looks good. So this data audit, we can close it and come back to the stream. The income field had a lot of different values. Of course, it was continuous. And let's say we don't feel comfortable having that amount of that range of values there, especially if we want to build a decision tree. So what I'm gonna do is that I'm gonna put those values into different bins or buckets. Under the fields operations, there are a lot of different pre-processing nodes that you can use. We have something called binning. All right, so the binning will take care of categorizing, or as it says, binning a field. So in this case, I open the binning node, I select income, okay, and then what it's going to do, it's going to build a new field that puts those original values into different bins. And you have different methods of fixed width or other options. I'm just going to go with the simple one. And I'm just going to ask it to, you know what, just put everything in like 5. 5, oh, come on. Okay, I'm just going to write down 5 buckets. All right. And if I go to, so by the way, it's going to add a new field, and then it says the extension is going to be like _bin. I go to the second tab, that will show me the bin values. Hit on the read values down here. Okay, so it's telling me that I'm gonna build 5 bins for you, and this is the range for each of the bins. Let's say it's fine, and again, you have the preview button. Let's see how our data will look like if we apply this pre-processing step. So yeah, as you can see, where was it? Okay, the income. The income now has been put into 5 different bins. A new field has been added. Okay. Don't forget that if you want to work with this, you have to exclude this one, and vice versa. We don't need both of them. Okay, we hit OK. So we put the incomes in 5 different bins, especially when we're going to build a decision tree. For neural network, the continuous are perfectly fine. It prefers the continuous values, so that's okay. But for decision tree, it might prefer to have it categorical variables. So one last thing would be part of the pre-processing. By the way, pre-processing sometimes take a long time to be able to explore and plan for it and apply it, and that's absolutely fine. Sometimes more than 50% of the effort goes for pre-processing the data. And the better you pre-process your data, the more reliable and robust results will come out of your models. We did plan to build classifiers. For classifiers, we know that we need to partition the data into training and test sets. So under the fields operations tab again, there is a node called partition. We add this partition here. We connect it, and let's open it and see what it's showing us. So it's saying that I'm going to add a new field called partition. I'm going to put everything, I'm going to split it into train and test sets. We're going to go with a 70% for the training set and 30% for test set. Okay. We're not going to split it into train, test, validation. In the cases that we have the option, we're going to use the cross-validation to build when training the model. But what this means is that it will take 70% of our data set randomly and only uses that 70% to train the model. It will not show the 30% test set to our model. It will not expose it to the model while it's building the model. And then when the model is built, it will use that, it will run through that test set on the model as unseen data and checks the performance of the model to see how good it actually worked. So everything else looks fine. Usually you have the option of providing a random seed number so that you can be able to reproduce it later on. In this case, I'm going to hit, let's click on preview again. Let me expand the window. All right, so another field is going to be added to our data set, and it's going to show us that whether the record belongs to training set or to the test set. This looks good. We're just going to close it. And finally, because we're going to build, okay, let me show it to you so that again you have an exact sense of like what I'm going to talk about. So again, I'm going to run through the data audit to see what happened to our data set and how they look like. As you can see, 2 additional fields have been added. The distribution of the bins for the income, and then the 70%, 30% partition that we have here. So if you remember, the approved field was the target variable that we had in this data set. So whenever we want to build a classifier, this is going to be the label of the records. Let me open the distribution of the target variable. It is 46% distribution. Okay. When we want to build a classifier, we want to make sure that the distribution is almost equal between the values on the target variable. This is what is called the data balancing. Okay, the data balancing helps us so that when we're building the model sees the same number of records for each different label. Okay, if the distribution is not balanced, let's say it's 40-60 or 70-30, then that means the model will see more records from the majority class, and it will probably or most likely will be able to learn the patterns from the majority class, and it will not do a good performance on the minority class. We don't want that to happen. So that's why it is very important that we provide a balanced data to train the model. And keep in mind that we're not going to use a test set to train the data. So we only need to balance the training set. Okay, so to train the to balance the training set, there are different balancing methods: the random undersampling, random oversampling, and the SMOTE. Okay. Actually, if you want to use undersampling and oversampling, again, there are no nodes in IBM Modeler. You have to end up coming to the data audit screen, open the distribution for the target variable, which where we are right now, and then again hit on the generate menu button, and you have some options here for balancing the target variable. Okay, it says balance node boost and balance node reduce. So there is a node called balance node in IBM Modeler, but it doesn't have the settings so that it can automatically randomly undersample the majority class or oversample the minority class. If you're not exactly sure what the differences between those two are, that means here in this case, no is the majority class, and then yes is a minority class. If we want to go with a random undersampling, it will, like here, we have 274 records for the minority class. It will randomly pick 274 records from the majority class. Okay, so it becomes equal with the minority class. The random oversampling does the reverse. It says the majority class has 326 records. What I will do, I will randomly pick some records from the minority class and duplicate it so that the minority class would end up having the same size, which means of the majority class, which means that the minority class will change from 274 to 326 records. It's around like 50 records will be randomly selected from the minority class and duplicated. That's what the random oversampling does. With SMOTE, what it will do is it will actually undersample the majority class a little bit, and it will oversample the minority class, but it won't duplicate the record. It will actually put it on a regression line and tries to come up with a more sophisticated method of oversampling. All right, it will synthetically build some records for you to oversample. Okay, so if we want to go, let's say we want to go with oversampling, you can select balance node boost, and then if you want to go with undersampling, you can hit the second one, which is reduce. In this case, I'm just going to go with the random oversampling. So I just select that, and I will close these windows. And it did add a new node. All right. This is a balance node. Just gonna bring it in here. Okay. And let's open it first and see what's inside. So what this does is that it says if the approved is no, just keep it. This is the coefficient of the number of records that have approved of no. But if the records that have approved of yes, I want to add like around 19%. That's why it's multiplying it by 1.19, so that we have more records that have the approved of yes. So eventually will become equal. And keep in mind, it's very important that you keep this checkbox checked so it only balances the training data. We don't want to balance the testing set at this point. Okay, we hit OK. We just need to connect the partition to this balance node. And okay, so if I connect data audit to this balance node, I will see that the target variable is still not 50-50. Why? Because we only balance the training set. In order to only see the training set, we go down here to the records operation, and the first node, which is called select, we add it. What it will do, it will just select a particular set of records. So we just open that. You have to define a condition if you want to include or exclude. In this case, we just want to include. If you don't want to write it down, you're not sure how to write the expression, you can hit this builder button here. And okay, so you can start building the expression on top of here, on this box here. So in this case, I just double click on partition. We'll add it there. I want to say when the partition is equal to the training set. If you're not exactly sure how the spelling, the typing of that is, what I would suggest, instead of you writing the values, there's a button here that can show you the actual values for the selected field. And yeah, so it's 1_training or 2_testing. We're gonna go with the training. Insert that. We can hit the check button so that it checks if it's valid. It is. So it became black, the color of the expression. We hit OK, and again we hit OK. Now at this point, I want to connect this select node to the data audit. And keep in mind that this will only select the records that have the partition of training, which means it's my training set. Okay, when I open this distribution graph for the approved target, yeah, so it tried to get it close to 50-50. If you remember, it was 54-46. Now it's almost 50-50. And now it's considered to be balanced. It doesn't have to be perfectly 50-50, but even if it's close, that's fine. So I just hit OK. We close this. If you wanted to, let me just disconnect this. If you wanted to go with SMOTE, under the records operation, the SMOTE, which is synthetic minority oversampling technique, you can add it there. And instead of the undersampling or oversampling technique that we showed you, you can go with SMOTE. And I'm just going to show you the window as well. So you have to select the target field here. In this case is approved. And then we're going to leave everything as default. We're just going to make sure it's going to balance the training data. And yeah, you can run that. And what it will do, it will oversample the minority class by building synthetic records. One thing that you have to be very careful when you're using SMOTE in IBM Modeler is that, let me open this type node here. If you have ordinal variables fields here, or basically not ordinal, categorical fields, but the categories are not string, are not characters, they're numbers. Like, let's say, I don't know, you have like a marital status, and instead of having like a married, divorced, widowed, and etc., or single, it's having 1, 2, 3, 4. Okay, so it's numeric, even though it's categorical. The SMOTE in IBM Modeler might not respect the categories and might end up having like a marital status of 1.5. The reason is that it puts it on a regression line, and eventually it will not snap it to the closest category. And this will cause problems for you later when you're going to build a model. So be careful. If you're going to use SMOTE and you have categorical variables that the values are numeric, they're not characters, then I would suggest that before using SMOTE, you first reclassify the values so that they're not numeric anymore. You can change them to anything else, like A, B, C, D, or whatever, something else that makes more sense. Then use SMOTE. That way, it will work correctly. Otherwise, you will face with failures during your modeling, in your modeling stage, and you will not understand what's going on. Okay, at this point, I'm not going to use SMOTE. I'm just going to leave it there. And you know what? So I'm just going to switch the size. Oops. I'm going to put it there. But, okay, come on. So I'm just going to keep this in a good shape as well. So at this point, my work is done pre-processing the data. Okay, I'm just going to leave this dummy data audit on the side as well. I didn't remove these nodes intentionally so that you know that we use them. You might want to use them as well during your work, and it might become handy. And now I'm going to, okay, let's see where we are. So we did partition, we did balance. Now we want to build a decision tree. All right. So we go to the modeling tab. It will show you all the different, or basically the favorite modeling methods there. But it has also categorized them here under supervised, which are the classification and regression ones, association, to the association rules, and segmentation, which are the clustering ones. So right now I'm going to go with supervised. I'm going to add a C5 method here. Okay, one thing that I always suggest is that before any of the models that you want to build, I always suggest to add a type node. Under the fields operation, add a type node. Okay, just gonna put the type node here. Let's bring this bit down. All right. If you remember, I said that it's possible that the fields might have different roles depending on what model you want to build. Okay, if I open the type node here, okay, we'll expand this a little bit. Yeah, so I can see that I have the income bin. When I have that, maybe I don't want to use the original income field. Okay. In addition, as you can see, for the partition field that was built, it automatically put a role of partition. That means it's not going to be input, it's not going to be target. It's going to use that to understand which records belong to training set, which records belong to test set. Okay. What I will do, I'll just click on the read values again here. Okay. And one thing, if you remember, the age, now it has a range that we mentioned that this is the acceptable range for us. And then for gender, which is fine. For gender, now we have two values, female and male. If you keep it nominal, it's fine. There's no problem with that, because binary or flag is actually, we can say it's a type of a nominal. It's a nominal with only two distinct values. But just for the sake of being crystal clear, I'm changing this to become flag. If you have set this to be flag at the very beginning in your source node, make sure that it doesn't exclude the other values while you're working with that field. It probably doesn't, but I didn't change it because I want to be very fragile working with all the steps and nothing goes wrong. It's very possible that if you start playing around a lot with one of the nodes, then it gets confused and not good information is transferred to the next node. So don't do that. Try to be as tangible and clean as possible when you're working with the nodes. Very important tip that I forgot to mention at the very beginning. Make sure your data set file is closed. Like in this case, it was Excel file. It should be closed all the time when you're working here in Ibm Modeler. Otherwise, you might face with different errors. Anyway, so I fixed that. I just wanted to be explicitly to be flag. Everything else was fine. In this case, now I have the income bin, which is it's not nominal because the bin is having a sequence. It has an order inside it. Like when someone belongs to bin number 5, I know that they have a higher income compared to one in the bin 2. So the ones that have a measurement of nominal, you want to review them and see, are they ordinal or not. Most likely Ibm Modeler cannot predict that, because that goes back to the meaning or the nature of the values inside that field, and a human has to actually address that. So this is ordinal. And for income, in this case, I don't want it to play any role, so just change this to none. Instead, I'm having the income bin to be input, the approved is target. This all looks good to me. Okay, so as you saw, we had to touch some of the fields, and now we give that to the C5 decision tree. So here in the first tab, either you can just say like use all the predefined roles, the node that comes in, or again you have the chance to here specify them. With the type node, it's more clear and more comprehensive, so I prefer to use a type node instead of defining them here. And then in the model, we're going to go with use the partition data, fine. Go with the decision tree, not a rule set. We're going to cross-validate, and the number of folds is going to be 10. I assume you're good with cross-validation. I'm not going to explain at this point here. We're going to go with a simple mode. If at any for any reason you end up having an overfit or any problem with the model that you've built, you can come back here and switch to expert mode and then start changing the parameters that are tuning and building the model. But at this point, we're just going to go with simple. and we're not gonna define any cost or anything else here. By default, the predictor importance will be calculated, which is good, and we're happy with that. So we just run this C5 decision tree. It's not a big data set, so it just comes back quickly. And now it built a golden nugget. We saw the golden nugget before. I told you at that point, golden nuggets are the models that have been built. So here it built a C5 decision tree. We can open this model and see how it looks like. So first of all, it shows us the ranking of the attributes. It's telling us children is contributing a lot in this decision tree to predict the approved status. And if I go to the viewer, I can actually see the decision tree. Okay, so this is the root node. It was split by the children, and it is saying, because we kept the children as continuous, we didn't change it to categorical, like ordinal type. It's showing us as bigger than lower than the number. But anyway, it won't be much difference in that case. Yeah, the record, the individuals that have 0 or 1 child will come here. And then the ones that have 2 or more will come here. Then you can follow these paths and see where it ends up. And like these leaps, they will show you like how it's gonna, like if someone ends up here, most likely what the status would be. So in this case, this leaf, the majority is with a status of no, even though not the entire records from the training set have a status of no. But if you follow this path and end up here, based on the splits that it had, 1, 2, 3 splits, you will predict it not to be approved for this loan or mortgage, whatever this is for, this data. And in decision tree, you can see that attribute can be used more than once, like children is used here to split, and then it's used here again here to split, or the income bin has been used multiple times. Okay. What else we can interpret here from the decision tree? Yeah, I think it's good enough. Any of these paths that goes to a leaf is basically defining a rule as well. Like it's saying if you have a lot of children and then you are on a low income, then most likely your request will not be approved. Your request for getting a loan or a mortgage. Let's say this is a request for a loan. And then you can see like if it makes sense or not, and if there are any other specific rules that you have discovered from the data. And this is the beauty of it, that you start discovering different rules and patterns from the data that might not be very clear or obvious without running this. And then with the summary, you can see, okay, the tree depth is 6, which sounds good. Most likely this model is not overfit. So these were some good information and interpretation that we had. Keep in mind that this ranking is not based on the information gained, while the splits in the C5 uses that. For the attribute ranking or the predictor importance, it ranks them based on sensitivity. So that means how much sensitive each of the variables, how much the input variables are. For example, if the children variable is showing up a lot in the tree, even if it wasn't the first split on the root node, then that means it's very sensitive, because it probably was coming up a lot, showing up a lot to split the nodes. That's why you will get a higher rank here. That means if you exclude children, then most likely your decision tree quality will reduce significantly, especially if the difference is a lot from the first to the second input variable. And then here also you can expand all the levels of your decision tree. It might be easier for you to read and find the paths that end up to the labels that you have if you want to extract the rules. One important thing is that the quality or the accuracy of this model, it doesn't show it here, unfortunately. So what we need to do is that from the output tab, there is a node called analysis, and we add that to the canvas. We connect it, we connect the golden nugget to analysis, and we open this. And the first one stands for the confusion matrix, further evaluations. If you want to calculate the area under the curve, you can set that as well. And you want it to separate by partition, that's fine. One thing related to the area under the curve, make sure that your target variable has to be flag or binary. Otherwise, Ibm Modeler is not able to calculate the area under the curve. Later on, we'll see that it's not able to plot the ROC curve as well. So it has to be a binary classifier. We run this. There are some other approaches when it's not a binary classifier. If you want to calculate the area under the curve, but you have to do that manually in Ibm Modeler. It doesn't have a built-in functionality for that. Okay, so yeah, here it shows you the correctness accuracy, which is the true positive plus true negative divided by the entire number of records in the training set. It's 89% or 90%, which is really good. And most importantly, you have to check that correctness accuracy on the test set as well. This is 88%, very close to the accuracy of the training set. That means that on unseen data, it actually provided 88% accuracy on the predictions. This is great. And if these numbers are close together, no matter if it's high or low, but if these two percentages are close, that means your model is not overfit. Even if you get accuracy like 60% and the test is also 60%, it's not a high quality model, but it's still the advantage is that it's not overfit. But if you get like 90% and on the test side you get 60%, it's no good. I mean, that means probably the complexity of the model is high, and the model has kind of learned a lot from your training set, and that's why it doesn't have the flexibility to do a good prediction on unseen data. So you have to go and reduce the complexity in the settings in your model and then see if you can help with that. But at this point, we're happy with this accuracy. This is the confusion matrix on the training set. This is the confusion matrix on the test set. You can calculate the sensitivity and specificity to see how much they are. It also calculates the area under the curve for us on training, which is 0.93, and then on test set is 0.92. This is excellent. Keep in mind that even if your accuracy is the correctness accuracy is high, let's say it's 90%, but then your area under the curve is like 70% or 0.7, that means that most likely the classifier is doing an excellent job on one of the classes, and it's very poor on the other class. So that means probably the sensitivity is very high and the specificity is not high. The combination have provided you with a high correctness accuracy, but because the area under the curve is sensitive to having a high sensitivity and specificity at the same time, if one of them is not high, then it will drop significantly. At this point, we see that this one is also, all of them are close to 90%, and this is great. So this means this is a brilliant model, and it's totally reliable, and we can use it. If you're interested to see the ROC curve, you can go to the Graphs tab. There is a node, I believe, evaluation node. Let me add this here. And then we connect the model to evaluation. We open this. Yes, it's the evaluation node. So the chart type, you can select the last one, which is the ROC curve. And yeah, we want it to be separated by partition. And I think the default is good enough. We run this. So this is the ROC curve on training set. This is on the test set. And this looks very good. The more the blue curve, which is our ROC curve, is tilted or shifted toward the top left corner, that means the higher the accuracy of the model. And the area under this blue curve was the 92% that we saw in the calculations. And that is one metric to check the accuracy of the model. And there are buttons here to export and print these graphs if you need them. There are other ways that you can, for example, you can again use the select node from the model to get the the training set, for example, or the test set, and then use from the output node, there's something called the matrix nodes. Use the matrix node and provide the x and y of the matrix so that you can manually build a confusion matrix if you want to. But again, with the analysis, it already will show you the confusion matrix on both the training and test set. Okay, one last thing in terms of evaluating the results from this model is that, let's say you want to go through the records manually and see how they have been predicted. What you can do is from the output, you can add a table node, okay, and then connect this model to the table node. And what it will do, it will actually show your data set in a table at this point. Okay, so let me expand it. It will show you the entire data set, not just the first 10 rows. Okay, so now you can see again 2 more fields have been added. One is the $C-approved, which is the predicted value for each record. And then this one is the confidence of the prediction. So, for example, this one is being predicted as yes, and it was yes, and it had a high confidence. It's correct. This one, although it was predicted correctly as no, but the confidence wasn't as high as that one. And this all goes back to the model that you have built, in this case a decision tree. In the leaf that this record has landed, the confidence wasn't as high as the other one. But the good thing is that it still is a correct prediction. And now this one is like a wrong prediction. The the status of approved was yes, and then it was predicted as no. And that is okay, because we're not having 100% accuracy. We're having a 90% accuracy, so it's possible that 10% error rate we see in our predictions. So that's how you can actually see the entire data set if you want to. So just to reorganize some stuff here, I'm going to remove this dummy data audit that we had. Probably we're not using it at this point. Move this stuff a little bit further here. A little bit here. Perfect. Okay, so now we're going to build a neural network. Again, as I suggested, let's have a type node. Okay, and we connect the last pre-processing step to the type node. We open the type node. In this case, it's going to be the same thing, the same situation that we have with this in tree. Again, the gender can be a flag. Now, instead of the income that was in the bin, I'm not going to use that. I'm going to use the original income, which was a continuous values, which neural network is fine with continuous. And that's it. Okay, now from the modeling, the supervised section, this is called a neural network. I'm going to add the neural network, hold it down, and then connect the type to neural network. Okay, now inside the neural network node, we'll just leave it as a use predefined roles, but you can go and modify it if you want. We're good with that. We go to the build option. There are some different settings that you can provide. We're going to build a new model. We're not going to retrain. It's going to go with a standard model. In the basics, we're going to use the MLP algorithm. We're going to leave this configuration to be automatic in terms of selecting the number of hidden layers and hidden neurons. The stopping rule, we're going to leave it as default, and we're not going to touch any other of the advanced. One thing I just want to make sure, keep in mind that if you still have missing values, it's going to, you have two options. Either you will ask it to impute it before building a neural network, or delete that record. Okay, by default it's the delete is selected. In our case, we already imputed and handled the missing data, so we're good. We wanted to calculate the predictor importance. Perfect. Let's run this. Again, it shouldn't take a long time. It's not a big data set. Okay, so now let's open this golden nugget. Let me bring it here. Okay, so in the output screen, we see that it does show the correctness accuracy on the training set for us here, which is 86%. This is also high. It's not as high as the decision tree, but it's very close. So this is also it's good. And it's told us that it used only one hidden layer, and in that one it had 7 neurons. The predictor importance, again, it's ranked based on the sensitivity of the input variables in the model. Children, again, is having the first rank, but now we can see the income is also as good almost as the children. You remember that we're using the real numbers for income compared to the binned version in the decision tree. Also, we can see the confusion matrix here. This is again on the training set. And this means both the sensitivity and specificity are both high together and close to the correctness accuracy. If you want to see the network, this is the network, and you can export it for your reports or anything else. 4, 5, 6, 7, 8, and 10. We had 10 input variables and 7 neurons, which sounds good. If the number of hidden nodes or the neurons were few, then probably it wouldn't be able to find the patterns very well. And if the number of this were more, especially if it was like more than the input variables, then it was a risk of overfitting. By the way, at this point, we don't know if the model is overfitted or not because we haven't seen the results on the test set. All right, so let's close this. Anything else that we wanted to see? No, we're good. So we close this. Again, we're going to add the analysis node. We connect the golden nugget to analysis. We open this. We check the first 3 checkboxes. We leave it the same. We run it. And yeah, let's see. Okay. Oops, what happened? So this is the window. Okay, so 86% correctness accuracy, which we already saw that on the training set. 83, this is good. So the model is not overfit, or they're very close. The area under the curve is again very high, 92% and 90%. So that means, as we saw, the sensitivity and specificity are both high. And that is also good. So you can go ahead and plot ROC curve, and you can again see the table if you want. If you don't want to see the entire data set, if you open the golden nugget, there's a preview button here which will show you the top 10 records. And again, the same thing. You can see this is the predicted values, $n-approved, and then the confidence of the prediction. Same thing that we went through with the decision tree. Okay, so let's see where we are. Decision tree, neural network. We did touch the confusion metric, ROC curve, and graph, the ROC curve graph. Now let's go with the k-means clustering. Okay, so with k-means, again, I'm gonna add the type node here. Okay, so you know that the decision tree and neural networks were supervised learning. And that means that we had a target variable. But k-means clustering is unsupervised learning. So it builds a descriptive model. That means that we shouldn't have a label or a target variable. Target variable doesn't make sense in a unsupervised learning model. In this case, because our dataset already has, we just are going to exclude it from the model. There could be some scenarios that there is actually no target variable in the dataset, and you use a cluster analysis to find different clusters, and then those clusters will actually become the labels, and then you can build predictive models on top of that. But anyway, it's not applicable to our scenario. Keep in mind that for unsupervised learning, we're not predicting anything, and we don't need separation or partition of training and test set. It's okay if you want to go with a training set, but it's not necessary. Even if you are going with the training set, again, you don't need to balance it. But we're gonna stick with the theory of the concept. At this point, we don't need partition, we don't need the balancing. Anything before that is good for us. So we just go from here. Maybe I should have kept this stuff on the right hand side and then switch this stuff to the left. Okay, so I a little bit moved around these nodes on the canvas so that we don't cross the arrows, they don't cross each other. So on the right hand side, which the pre-processing ended up partitioning and balancing it, we had all the predictive models here, and then because we don't need the partitioning and balancing for the unsupervised, and we're gonna continue the work from binning, which would be the last pre-processing step, and then go for clustering here. I'm gonna use the left side of the canvas for the unsupervised. Again, you don't have to put everything in one stream and in one project. You can break it down and just have the pre-processing in one stream and then export it, and in separate streams you actually do your different modelings and all that stuff. But because for this demonstration I want to show everything in one place, I'm going to keep it organized this way. So let's go and down to segmentation, and let's add k-means. Okay, so with k-means, you know that you are the one that have to specify what the k value is going to be, or basically how many clusters you want it to build. If you don't have any idea of, like, I don't know, like how many clusters I want it to build, so you can start with 2, then just incrementally increase it, like 3, 4, 5, 6, and see which one provides a better result. Or there's an option in IBM Modeler that if you go back to under the modeling tab, click on all, then it has auto cluster node, which I'm going to add it to the canvas. What this does, it's actually going to build different clustering models, including k-means. There are other clustering as well, like the Kohonen, which is the SOM, I believe. The two-step is another clustering model that uses hierarchical clustering inside it, and then it tries to suggest which k would be the best, has the highest quality if you want to go with k-means. We will run it, you will see it, and it's not very difficult to understand. But before that, again, as usual, we have the type node here. For this one, what we want to do is that, keep in mind that you can have all these input variables. I'm going to forget about this binning for now, and the target, if you have a variable with the role of target, it will automatically be excluded from your clustering models. So you can just leave it as target, or you can change it to none. I'm not going to change anything else for now, and I'm going to connect this type to auto cluster and just quickly go and see what this auto cluster has. We didn't partition the data. As you can see, we have had a branch off the binning, so we're not partitioning. We don't need it for the clustering, so we just remove that. It will rank the models based on the silhouette average, which is the quality measurement for the clusterings. And yeah, let's just run this quickly and see what it brings us. Okay. So, let's see. It is suggesting that if you want to go with k-means, let me maximize this page. If you're going with k-means, it's suggesting to go with number of clusters of 5, which probably will give you a higher silhouette average, which is the quality, and the other information. We're not going to look around all that information. The only thing that we want to get is this one, number 5. So cluster of 5s. Then we close this. Let me just leave this down here. And now, way to work this guy. We want to build k-means clustering. We're not partitioning it. The number of clusters, we're going to go with 5 because the auto cluster suggested with 5 clusters you'll probably end up having higher quality. And you can check this generate distance field. I will explain what it means and leave the rest as default. Under the expert, you can switch the expert mode and define the stopping rules. But by default, with a 20 iteration on the k-means, or the tolerance of, I believe, is 0.5 or 6 zeros and then 1 of change, it will stop. Okay, let's run this and see what it will create for us. Let's put this here. Okay. Let's see. So it did build a k-means clustering, had 10 inputs, usually 5 clusters. The quality is 0.1, the silhouette average, which is in the poor section. This is the definition that Ibm Modeler has, so you can interpret better the quality of your clusters. And other information of the size of the smallest cluster, which is 14% of the data set. The largest is 26. The ratio between them is 1.8. Keep in mind that for k-means clustering or normal most other clusterings as well, if you have the number of input variables are not few, it's very unlikely that you can end up having high quality clusters. Okay, so what this is saying is that how much these clusters are cohesive inside each other and separated from each other. And the more they're separated, the better. But in this case, because we're having 10 input variables, every data point is becoming unique, and the distance between them is not kind of separable, and everyone's kind of separated from each other equally almost, because they have 10 dimensions. On a space of 10 dimensions, every data point is in a very unique location. But anyway, this still doesn't stop you if you want to go ahead and interpret what clusters have been built. Okay, first of all, these are the size of the clusters you can see in the pie chart here. Then down here you can switch to clusters, Okay, I'm gonna expand this page here a little bit. Before I go through this, on the right hand side, this drop down, you can select the predictor importance. This is not a predictive model, so Ibm Modeler is using the predictor importance terminology just to be consistent with the predictor importance that we saw on the classifiers, but as you can see, it actually is the input importance. And in this case, the saving account is playing a big is actually playing a big role in actually characterizing the clusters. We will see what that means a little bit further, but it will provide you with some ranking as well here based on the amount. If I want to say it in another word, if any of those input variables are helping you or the model to have a more distinguished characteristic in the clusters that differentiates the clusters, it will have a higher ranking in this importance list. So let's see it here. So in this first cluster, which is cluster -2, the saving account variable, which is top in the list here, it's saying that if I click on it, it's saying that all the records in this cluster, all the individuals, they do have a saving account. Okay, so that's why you can actually label this or describe this cluster by saying like this cluster includes people that do have saving accounts. Let me show you another example. Like the next one is having a car, and then here you can interpret this by saying like most of the individuals here have car, but still there are people that don't have car as well in this cluster. The more you go down in overall during the cluster, for all clusters, the less distinct and separate the distribution is. So for merit, again, here you can interpret and say this cluster is, if you want to start describing, it says includes people that have saving account, and most of them have cars, most of them are married, most of them are male. We can't say much about the mortgage, although keep in mind that in your data set, this is the overall count and overall distribution on the data set. The majority, they don't have mortgage, okay? But in this case, in this cluster, most of the people do have mortgage. So relatively, 50% out of the overall, the individuals that have mortgage are in this cluster. So it's fair to say most of them do have mortgage. And then for income, it's all over the place. You can't describe anything about the income of this individuals in this cluster. So as you see, when we go down, the less likely we can have a description coming out of it. This is about the age, same problem. This is about the checking account, although most of them do have checking account, but again, keep in mind, looking at it relatively to the overall distribution, this looks like to be like the same distribution of the overall. So you cannot say much about like the checking account status of people in this cluster. Same thing about children. Again, as you go down, the less likely you can use these variables to describe your cluster. But if you are up here, like on the next cluster, again, you have people that have saving accounts, and it's more sharp to actually cut the edges and describe the clusters using the top variables. But again, in overall, this clustering model didn't have a good quality, and that's why it's not a very good model. Okay, so one way that you can build a better clustering model is that you reduce the number of input variables. If you have used all the input variables and you've built this model, one way is that, let's say I just want to pick the first three, the top three important variables and see what happens. So saving account, having a car, and being married. In this case, it was the high rank. So I'm just going to close this. Okay, what is this? All right. And I'm going to add another type node. You can also add a filter node, but keep in mind that if you add a filter node, it will filter those variables that you don't want. And later on, if you want to interpret the clusters using the variables that were not part of the modeling, but you still want to see how they look like, you will lose them. I will show you an example later on about this issue. So I connect from the beginning to the type here again. And now, this time, what I'm going to do, I am going to, first of all, I'm going to change. So what you can do, you can select one row or just select everything and then change the role of one of them to none, and we'll change for all of them. Okay, easier way. And now, so what was the top three? If you can remember, saving account, car, and married. So saving account, input, car, input, and being married. So I'm using the top three from the previous k-means clustering to be the input. And let's add the k-means again. Let's connect this. Or you could have basically came to the first field and just excluded all of them and reran that model. But I just wanted to keep that model, that's why I just added a new one. I'm going to generate distance field again. I didn't show it last time what that meant, but this time I'll probably show you how it's going to look like. Okay, super. Now we have this golden nugget. Okay, now look at this. So the quality increased significantly. It went to 0.7 because the number of input variables now are few, and we actually used the experience from the previous model, and we used the top three important ones. So they were the best three variables to provide good separate clusters. Okay, and so that way you can have a high quality clustering model. And now you can see, you can start interpreting them again and see like, okay, so this cluster are people that they do have a car, they do have a saving account, and most of them are married. Okay. Because I didn't filter the other nodes and I just changed the role to none, when I preview the data, or I can connect a table node and see the entire data set. I still have the other variables or the other fields there as well. So if I want to build graphs or any other analysis on these clusters and evaluate how the other variables look like, I have access to them. But if I filter them, I didn't have them. So that's one thing that you have to keep in mind. Second is that, again, you can see two fields were added. One of them is the cluster label. The other one, which says like this record belongs to cluster 1, this belongs to cluster 3, and etc. The other one is because if you remember, we checked to generate or calculate the distance field. This field was generated because of that. What this means is that this record, which is a data point, the distance of it from the center of the cluster that it belongs to, which is cluster 1, is 0.5. This is the distance of the record to the center of its cluster. Maybe in some cases you might need it, like for example in this case, this means this record, which is in cluster 4, is almost in the center of that cluster. And the more they're in the center, the more they're cohesive. And if the distances are large, that means these were the points that they were finally assigned to this cluster, but it's less likely that they are similar to the other individuals in that cluster. Okay. So that's how you can build a high quality clustering model. Okay, now let's say I want to check the distribution of the approved status in the clusters that I built. How can I do that? So one way is that we build a distribution plot out of this model. So we connect this to the distribution. We open this node, and we want to actually see the distribution of the clusters, and inside each cluster we want to check the approved status with by separating with colors. If I run this, then you can see that in all the clusters, it's almost half. I'm having approved yes and no. So there's no much information that I can get out of this, of saying like, okay, for example, in cluster 1, the majority or most of them or all of the individuals in cluster 1, they have like a status of yes for their loans being approved, or any other variable that you want to actually go and check. And this is one way that you can do it. This is the graph of the same table. Okay, as the last experiment on the model, I'm going to again add a type node here and add a k-means clustering. This time I'm going to do a very specific experiment so that again I'm going to set the row to none for all of them, and I'm going to only include I'm just going to include the 3 continuous variables that I have here, and then connect this to the k-means node a little bit down here, and I'm gonna go with 5, that's fine, and run this model. Now again, I'm having 3 input variables, and specifically all of them are continuous. This time I'm having a clustering model with a quality of fair, which is okay, not bad. And again, if I go and check the clusters one by one, it might give me some information of, like, in the first cluster, I'm having the individuals that don't have children or just only have 1 child. Their income is toward low, and their age is toward being young. So it is somehow being able to describe the clusters, and they're kind of being separated. But how can I visualize this to see how they are separated? Under the Graphs tab, there is a node called Plot. Let's add this Plot node here and connect the model to this plot and open it. In this case, you can plot a 2-dimension or 3-dimension. I'm going to go with 3-dimension and include only the 3 input variables that I have. Because I didn't filter the other variables, it's still showing them to me. I still have access to them, which is good. I'm going to show you in a second why. These were the 3 continuous input variables that I had for the clustering. You can provide some properties for this graph. The color, I'm gonna say set the color of the data points in this plot based on the cluster labels, and I'm gonna say for the shape of the data points, use the approved field, which is my label field that I had. I'm just curious to know how the clusters look like in this case. If I can have any interpretations, like any specific clusters include mostly from any of the classes that we have, just for my further investigations and evaluation. And we run this. It comes back with a 3-dimension space that age, children, and income. The reason that I decided to go with the 3 continuous variables was because I wanted my data points to be like all over the place in the space. If you go with categorical, you can still plot this graph, but a lot of the data points will be overlapping each other, and it won't be like scattered all around the space. And then keep in mind, because it's 3-dimension, first of all, start moving around the perspective that you are looking at. Okay, this looks good. All right, so now look at this. I can see that each of these colors are actually showing the different clusters that I have, because I use it to separate the colors of the data points. And then the shape, the one with O was a status of no, and then the square is approved of yes. So the cluster, the green cluster, is showing me that these are the people that have more children and their income are low. And in terms of age, if I want to look at it, their age is almost toward being young, but still there are some data points that are not close to the center of the cluster. And that's why the quality of my cluster is in the fair zone. It's not in the good zone, and the quality is not very high. But still, you can visualize your clusters and interpret it visually here as well. Or, for example, let me see if I have any of the clusters, like even like the green. As you can see, most of them, the majority, are circle, and there are few squares that you can see. And that kind of makes sense. So that says like, okay, the ones that have more children, their income is low and they're young, they probably are among the high risk, and most likely their loan hasn't been, that's why their loan hasn't been approved. Okay, that can be an interpretation that you can get out of this 3-dimension graph. You can export it from any of the views that you believe it's showing well, and yeah, so that's a feature that you can visualize it. Your clusters in IBM Modeler. Wow, our canvas is too busy now. I think we're done. One last thing would be if we want to reuse the models, and let's say the C5 decision tree that we built, which was over 90%, I think, accuracy, or around 90%, was very good. And now we receive a new batch of data from the same source. So it has the same variables, all that stuff, and it's the same batch. And now I want to run it through this model to actually predict the status of these new records that we have received, and we want to use this model to predict. So keep in mind that because you ran some pre-processing steps, the same pre-processing, or I should say the applicable pre-processing steps, should be again implemented on the new set of data as well. And then after that, you can you can actually feed that model with that data and get the results. Okay, let me just scroll a bit down here. We move from all this mess up there. Let's say I'm going to add a source node, the Excel file, and I'm going to use, just for our experiment, the same data file. I preview it again just to make sure it looks good. Perfect. So what I'm going to do is that I'm going to use the same pre-processing steps that I had, and I will copy them. And down here, I will paste them. Okay. Yeah. Okay, so because it's important that when the new batch of the data arrives and you want to predict it using any of those models that have been built, again, of course, you can add a data audit node and go and check that if they look good or not, what type of pre-processing they need. But it's important that if they need the same pre-processing, in this case, because I'm using the same data, let's say this is a new, but again, the same type of pre-processing is needed, you use the same nodes that were built originally on the data that you used to build the model. so that they follow the same parameters and the same rules. Okay, so you connect that to the pre-processings that you want to go with, and then at this point, what we can do is let me use this data audit node as a dummy. And by the way, I forgot, because I added in this new source node, I didn't go and actually set the measurement and roles for them. Even if it's a new set of data, but you still have to do the same thing. And then this is target, and everything else we just keep it as is. We still have issues with the age and gender in this new set of data that we have received. So we're going to reclassify, we're going to fix them, define the missing values, we're going to impute it, we're going to bin the income field, and then now we can run it through the data audit, and just to make sure that the same pre-processing is done. This looks good, the gender looks good, and it's perfect. Well, in this case, so that it can make more sense, what I would say is that let's filter out the approved, because in reality, when you receive a new batch of unseen data, it doesn't have the it doesn't have the target variable. You want to predict it, so this basically has to be filtered out. And as you can see, it was filtered out here, and yeah, so now it reduced to 11 fields. Now I want to run this pre-processed data on this golden nugget. So I just drag it and I connect to this. So remember that in this case, we didn't have the labels for the records. We didn't have the target variables. So we cannot run any analysis on it, because there's no way that you can check that if the predicted values are matching the actual observations. So what you can do is that you just add a, let's say, a table, and you connect it from the model to the table, and you run this. Okay, so now it will show you that for each record, this is the status that it has predicted for you. Okay, so it used that model to predict these information. Again, because these records didn't have any labels, we cannot check that if it's correct or not. And this is the whole purpose of building a predictive model, so that later on when you receive new data and you want to predict, then you rely on that model with 90% accuracy, that you trained it and you ran it on a test set, because on the test set we knew what was the actual observation that we could have compared with the prediction values, and we were happy with that. Now on this new batch of data that we don't have the actual result and we want to predict it, we rely on it, and we predict their status. Okay, so that's how you actually use the models you've built in IBM Modeler on the new batch of data. You can actually right-click on these models that you've built as well and save them with specific file extension, I think called it .gm, if it can be used anywhere else as part of being embedded to a program, or you can export it and it will export it as an XML for you. I'm not sure if it has other types. No, it's just XML. And when you save that, I have already exported one version, and it actually puts that model that was built in an XML format. So that again, if you want to embed it and read it in your, let's say, another computer program that you have when you use this model, you can actually use it outside Ibm Modeler as well. Okay, I hope you enjoyed it, and good luck with your experiments and projects. Take care.